Okay, let's dive right into this explainer. You know, in the world of basic optics, it is incredibly easy to get bogged down in the math. We've all been there. You memorize formula after formula, and before you know it, you've completely lost sight of the actual physical reality happening behind all those equations. But today, our goal is to build a truly geometric, intuitive understanding of an absolute cornerstone concept for your board exams, transverse magnification. We're going to strip away the complex algebra and reveal the elegant geometry underneath it all.
In the past, we've focused heavily on where light actually focuses. We spend a ton of time answering that first primary question, right? Where does the image form? Using the concept of vergence. But today, we're pivoting to a completely different question. How big is the image compared to the original object? That single simple question is the absolute foundation of transverse magnification. And by the end of this explainer, you're going to see exactly how we solve it.
Here is our quick roadmap for today. We'll cover the foundation, the measurement problem, the geometric solution, and finally, the grand synthesis.
Part 1, the foundation. Let's lay the absolute groundwork.
Here is an absolutely crucial board examination pearl. You have to mentally separate vergence, which dictates location, from magnification, which dictates physical size. This distinction is just so important because it's incredibly common to conflate the two. Keep in mind, an image can form exactly where we expect it to while still being way larger or way smaller than the original object. Say you've got a highly curved lens and a relatively flat one. By tweaking where you place the object, you could actually force both of those lenses to project an image in the exact same spot on a screen. But the physical sizes of those two images, they'd be drastically different. So always treat location and size as two entirely separate puzzles to solve.
Notice that we are purely comparing the vertical height of the image arrow to the object arrow. So whether you see it called transverse magnification, lateral magnification, or linear magnification in a textbook, don't let it throw you. It's the exact same thing. It purely refers to comparing the vertical physical height of the image to the object. And notice, there's absolutely nothing in this basic definition about lens power or diopters yet. It is just a purely geometric relationship comparing physical sizes in space.
Part 2, the measurement problem. Let's look at how this straightforward definition creates a real-world clinical headache.
So, the textbook physical definition is simply image height over object height. Imagine an object standing upright in front of a thin plus lens. Light rays pass through and boom, a focused image forms on the other side. Sure, if we had a perfectly drawn ray tracing on a piece of paper, we could literally just grab a physical ruler, measure the two heights, divide them, and we'd have our magnification. But think about clinical optics. You can't exactly hold a ruler up to a patient's retina to measure the image height of a slit lamp beam. Real-world optical setups and definitely board-style questions almost never give you those actual physical heights to measure. Instead, they'll give you lens power, object distance, or maybe vergence. So ask yourself, if someone only gave you incoming and outgoing vergence right now, could you find the magnification? At this exact point in our explainer, the honest answer is probably no. But we are absolutely going to fix that.
Part 3, the geometric solution. This is where high school geometry delivers a massive aha moment.
If we strip away all the extra, distracting light rays from our model, we reveal a very simple, very familiar geometric shape. We're left with just the nodal ray passing right through the optical center of the lens and the horizontal lens axis itself. Now, that central nodal ray is special. It passes straight through that optical center without being bent or deflected at all. It basically creates a pure, straight line stretching all the way from the tip of the object right to the tip of the image.
And look at that! This brilliantly illustrates two hidden similar triangles meeting right at the nodal point in the center. Because that nodal ray passes straight through unrefracted, the angles it forms with the primary visual axis on both sides of the lens are identical. They're opposite angles at the vertex. So because they share that exact same angle, and because both the object and the image stand perfectly straight up, forming 90-degree right angles at their base, we have two perfectly similar right triangles.
Now, because these triangles are mathematically similar, the ratio of their vertical heights, which is image height I over object height O, absolutely must equal the ratio of their horizontal lengths. And let's think about what those horizontal lengths actually are in optics. They're literally just the image distance, little v, and the object distance, little u. So I over O equals little v over little u. This is a real game changer.
Suddenly, we don't need a physical ruler for vertical heights anymore. If we just know how far away the object is and how far away the image forms, we can perfectly calculate transverse magnification using distances alone.
Part 4. The grand synthesis. It's time to connect this geometric truth to the master formula of clinical optics. Let's bring back the classic Vergence formula. Big U plus P equals big V. We know incoming vergence plus lens power gives us outgoing vergence. And, recalling our fundamental training, distance is simply the mathematical inverse of vergence. So the object distance, little u, is exactly equal to 1 over big U. And the image distance, little v, is equal to 1 over big V.
Okay, here is where the absolute magic happens. We can just substitute those vergence inverses directly into that distance ratio we just established. Let's walk through it. Take our geometric formula, little v over little u. Instead of writing little v, we swap in its inverse equivalent, 1 over big V. And for the bottom, instead of little u, we drop in 1 over big U. We are literally just swapping distances out for vergence.
And the algebra elegantly simplifies to our grand conclusion. When you divide a fraction by a fraction, that math just flips. 1 over big V divided by 1 over big U becomes big U over big V. Magnification is simply the incoming vergence divided by the outgoing vergence. We have completely solved our measurement problem from earlier. We don't need rulers for heights, we don't even need tape measures for distance. All we need is the dioptric vergence.
So let's appreciate how cleanly we just evolved from a basic physical measurement to a super easy-to-use clinical vergence ratio. Step 1. We started with the raw physical definition, image height over object height. Step 2. We use the geometry of similar triangles to prove that height ratio perfectly equals the image distance over object distance. And then Step 3. We use divergence law to prove that the distance ratio mathematically flips to become incoming vergence over outgoing vergence.
This master summary proves that whether a board question gives you physical heights, distances, or vergence, you now possess the unified key to unlock the exact same magnification. Got physical heights? Just divide them. Clinical vignette only gives you distances? Divide those. Only given vergence values in diopters? Simply divide incoming by outgoing. They all represent the exact same geometric reality, just expressed in different units.
I'll leave you with this final thought to ponder. How does this elegant geometric principle actually manipulate the images you see in a slit lamp every single day? Magnification isn't just some abstract equation to memorize for a test. It physically dictates retinal image sizes, your field of view in indirect ophthalmoscopy, and real-world contact lens optics. It's the whole shebang. So next time you sit down at an optical instrument, think about those hidden similar triangles and vergence ratios working behind the scenes. Until next time, keep exploring.